chapter 12 is all about linear regression and correlation. So 12.1 is a review of linear equations. So the linear regression for two variables is based on a linear equation with one independent variable. The equation is of the form y equals a plus bx. Notice this looks very familiar. All the way back in your Algebra 1 class, you learned that y equals mx plus b. So in this case, a and then this b would represent the y-intercept. M, or the b in this equation, basically the coefficient of x is the slope. So a and b are constant numbers. You'll never have variables in that spot. The variable x is the independent variable and y is the dependent variable. Typically, you choose a value to substitute in for the independent variable and then solve for the dependent variable. So you pick 1 to be x and you plug that in and to find y. Both of these are examples of linear equations. You might also see y equals 2x plus 3 or y equals negative 0.1x plus 1.2x. The graph of a linear equation of the form y equals a plus bx is a straight line. Linear means line. Any line that's not vertical can be described by an equation like y equals a plus bx or y equals mx plus b. So if we want to graph the equation y equals negative 1 plus 2x, negative 1 is the y-intercept. So you start at negative 1 on the y-axis. 2 is your slope, so you go up 2 over 1, up 2 over 1, up 2 over 1, which is hard to see on that graph since it's doesn't have every individual tick mark. Aaron's word processing service does word processing. The rate of services for 32 hours per hour plus a $31.50 one-time charge. The total cost to a customer depends on the number of hours it takes to complete the job. Find an equation that represents the total cost in terms of the number of hours required to complete the job. So your total cost is your dependent variable. The number of hours is the independent variable. In this example, the total cost would be you have a one-time charge of $31.50 plus an additional $32 per hour. So $32 times the number of hours, which is X. So you could then use this equation to find what's the total cost if it takes 5 hours, or questions similar to that. All right, slope and the y-intercept of a linear equation. So in this equation, A is your y-intercept, B is your slope. I kind of already talked about that on the previous slide. From algebra, recall that the slope is a number that describes the steepness of a line. So for example, this is a positive slope. This would be a slope of 0 because there's no rise. And then this is a negative slope. The y-intercept is the y-coordinate of the point 0a. So any y-intercept will have an x-coordinate of 0. Svetlana tutors to make extra money for college. For each tutoring session, she charges a one-time fee of $25 plus $15 per hour of tutoring. A linear equation that represents the total amount of money Svetlana earns for each session she tutors is y equals 25 plus 15x. What are the independent and dependent variables? Well, the 15x is representing $15 per hour. So the hours that she tutors is the independent variable. X is always the independent variable. Y, or the dependent variable, is representing the total money that she earns. So, and that makes sense, right? The total money she earns depends on how many hours she works. What is the y-intercept and what is the slope? And then interpret them using complete sentences. The y-intercept is 25. So that means that's representing the one-time fee of $25. Or she earns $25 before she starts tutoring. The slope, or M is what I like to use for slope, is $15. She earns an additional $15 per hour tutoring. All right, so that was it for linear equations. Hopefully a lot of that was review from your algebra classes. 12.2 is about scatter plots. So scatter plots are a common and easiest and one of the easiest ways to display the relation between two variables x and y. So in Europe and Asia, m-commerce is popular. M-commerce users have special mobile phones that work like electronic wallets, as well as provide phone and internet services. Users can do everything from paying for parking to buying a TV set or soda from a machine, to banking, to checking sports scores on the internet, etc. For the years 2000 through 2004, was there a relationship between the year and the number of m-commerce users? Construct a scatter plot. So X is the year, Y is the number of m-commerce users in millions. What's nice is your graphing calculator can do this. So on my graphing calculator, you are familiar with the list, so we're going to do stat, edit, and we are going to clear our list out. Your independent variable, so in this case the year, goes in L1. And our number of users, which I believe is in the millions, is our dependent variable. So our data is on our list. Now we need to turn our stat plot on. Above your y equals button, there's a blue stat plot. So you're going to hit second stat plot. And we're going to go into plot 1. And first we're going to turn it on. So I'm going to hit enter on. This first is the first option here is a scatter plot. Our X list is L1, our Y list is L2. You can pick what you want to mark your points. You can also pick the color. After that, I'm just going to go to Y equals and see I have stuff typed in. I need to make sure that's cleared. And I can see my plot 1 is turned on here. So I'm going to go to zoom. Zoom stat number 9 will fit the window for your scatter plot. And I have a setting turned on so that way I can see the table and the scatter plot. But you can see that there is a correlation here. It all is trending close to a line. So this would be called a linear correlation. And it's all trending up. And so we could tentatively say that the relationship between the year and the number of users is as the years increase or more years pass, the number of users also increases. So a scatter plot shows the direction of a relationship between variables. A clear direction happens when there is either high values of one variable occurring with high values of the other, or high values of one variable occurring with low values of the other. You can determine the strength by looking at the scatter plot. So like here, this is a positive, strong linear pattern. It's trending upwards and it's really close to a line. This would be a linear pattern with one deviation. It looks like a line, but there's this one weird spot that's pretty far away. This is a negative strong linear pattern. It's going down and it's really close to a line. This would be a negative linear pattern that's pretty weak. It is going down in a line, but it's pretty wide in terms of like the vertical difference or direction. So like here, we're really close to a line. This is still a line through the middle, but they're pretty far away from it. This is an exponential growth pattern. It looks like an exponential graph. This would be no pattern or no correlation. There's not a relationship between the two variables. If your data shows a linear pattern, you can calculate the line of best fit with linear regression on your graphing calculator. And so that can give you a great prediction equation. So how to get that regression equation? Data will rarely fit a line exactly. So we're going to find the line of best fit, or it's also called a least squares line. So your calculator can do this for you. So we're going to put this information from a random sample of 11 statistics students, where X is the third exam score and Y is the final exam score. So can you predict the final exam score of a random student if you know the third exam score? So if we look at the scatter plot, we see this has a pretty positive, strong correlation. And so I can use my graphing calculator. So I do stat edit. And I'm going to put this data into my graphing calculator. I will say, as I'm typing this in, the most common mistakes I have from students is mistyping, like putting 68 instead of 67, or even sometimes just putting a 6 and hitting enter too early and dropping the 7 completely. So like there, I accidentally typed in an extra number. So it is worth the time to double check all of your numbers. Another great way to just check that you're on the right path is make sure you have the same number of elements in L1 and L2. So my stat plot is still turned on. I'm going to do zoom stat. And you can see that same scatter plot that I had on the notes. To get the least squares line, or the line of best fit, your calculator will do this for you. Stat, go over to calc. And you want linear regression. Now you have two of them. 4 and 8 are the same thing. The only difference is like 8 matches the textbook, A plus BX. 4 is the same thing, it's just AX plus B. That's what you typically see in slope-intercept form. That's the one I use. Just keep in mind, your X list is L1, your Y list is L2. We do not have a frequency list. And you may want to store your regression equation. I like to store it in Y1. So to do that, vars, go over to yvars, function y1. And I'll show you what that does here in a second. But that gives you your equation. So our equation for this is y equals 4.827, that's our A, x, plus b is negative 1.7, or negative 173.513, etc. If I go back to my graph, it now has that line through there because I stored it in Y1. If you store it in Y1, it also makes plugging in values for X significantly faster. So that's how you would do this with the graphing calculator. I would always recommend using the graphing calculator to do this. The doing it by hand method is a little messy. So let's say this has said, predict what someone gets on the final exam if they scored a 73 on the third exam. A fast way to do that would be, if I'm on the graph, I can hit trace. And right now you can see I'm on the plots. I want to be on the line, so I'm going to hit the down arrow, and now I'm on the line. And I can plug in 73 for X and hit enter. So I would predict a score of 178.89. These next few slides go over how to do it by hand, but since I just showed you how to do it with the graphing calculator, I'm not too stressed about them. All of this is from your textbook. One thing I do want to point out is the error, or the residual, is how far from the line of best fit that the data point actually is. That could become important later on. Your least squares criteria, again, you're using your graphing calculator to do this. Okay, so slope. The slope of the line B describes how changes in the variables are related. It is important to interpret the slope of the line in the context of the situation represented by the data. You should be able to write a sentence interpreting slope in plain English. So the slope of the line of best fit tells us how the independent variable y changes for every 1 unit increase in the independent example, or the independent variable x on average. So that last equation that we just did on the graphing calculator, the slope of the line was 4.38. So for every 1 point increase in the score on the third exam, because that was x, the final exam score, y, increases by 3.83 points on average. Positive slope, so this final exam score is increasing. Negative slope, the final exam score would be decreasing. Okay, the correlation coefficient R, here's how to do it by hand. Your graphing calculator does it for you. R is always between -1 and +1, and it can equal -1 or +1, but it can't go past those. The size of R indicates the strength of the linear relationship between x and y. If R equals 0, there is no linear correlation, so the scatter plot's all over the place. If R is equal to 1, there is a perfect positive correlation. If R is equal to -1, there's a perfect negative correlation, meaning that the points are exactly on a line with either a positive or negative slope. R is like a continuum or an interval. So if you have -1 to 1 and then 0 in the middle, this is a perfect negative correlation. This would be like a strong negative correlation, so like -0.9. A weak negative correlation would be like a -0.4. Weak positive correlation would be 0.4. Strong positive correlation like 0.8, 0.9, and a perfect positive correlation. If it's a positive correlation, that means that when x increases, y increases, so it's going up. Negative correlation means as x increases, y decreases, so the slope of your line is going down. The sign of R is the same as the sign of the slope. So positive slope means positive R, negative slope means negative R. Like I said, your calculator can do this for you. R squared, again, your calculator can do this for you, is the coefficient of determination, and it is the square of the correlation coefficient that we just talked about. Usually it's stated as a percent rather than a decimal form, so you might get R squared is something like 0.4397, so we would say approximately 44% for R squared, because we would move that decimal point to the right twice. R squared, when expressed as a percent, represents the percent of variation in the independent variable that can be explained by the variation the dependent variable that can be explained by the variation in the independent variable. So if it's 44.4%, we'd say approximately 44% of the variation in the final exam grades can be explained by the variation in the grades of the third exam. So then the 1 minus R squared would be 56% of the variation cannot be explained by the variation of the third exam. Okay, so scuba divers have maximum dive times that they cannot exceed when going to different depths. The table shows the different depths. Use your calculator to find the least squares regression line, and predict the maximum dive time for 110 feet. So I get out of my Keynote and go to my graphing calculator. So we're going to go to Stat and then Edit, and we're going to clear our list out. Okay, so I have the data from our notes here. So I go to Stat, Calc, Linear Regression. So either 4 or 8, it doesn't matter. X1 or X list is L1, Y list is L2. Again, I do highly recommend storing your regression equation. So vars, go over to yvars, function y1, and hit calculate. So our equation is y equals negative 1.114x plus 127.238 for our y-intercept. If I go to y equals, you'll see my plot 1 is still turned on from the last couple examples. It copy and pasted that equation into y1. I'm going to do zoom stat to see my scatter plot. I can see that it's a relatively strong negative correlation. Now, this one did not give me my R value, so I'm going to go over how to turn that on. So I'm going to go to second, catalog, which is 0, and I'm going to scroll down until I get to diagnostic. And we want the diagnostic on. So I'm going to hit enter on that. I'm going to hit enter. And then now if I run that same linear regression, I already have it stored. Now it gives you your R squared and R. So you can see R is negative 0.96. That's a really strong negative correlation. R squared is 0.927, so approximately 93% of the variation of the maximum dive time can be accounted for due to the variation of the depth in feet of the dive. Okay, this example had asked us to predict the maximum dive time for 110 feet. I can do that by plugging 110 feet in for X in my equation and just doing it by hand. Or, because I stored this in Y1, I can put Y1, and then like function notation, if I wanted to find F of 110, we use parentheses. So if I want to find Y1 of 110, I'm going to put that in parentheses, and it plugged it in for me. So your maximum dive time for 110 feet would be 4.67 minutes. All right, so continuing with that same third exam, final exam example. We examined the scatter plot. We showed that the correlation coefficient was significant. We found the equation. So suppose that you want to estimate or predict the mean final exam score of a statistics student who received 73 on the third exam. Well, you would plug in 73 for X. Since 73 is in between the X values that we had in our table. So what would you predict for a student who scored a 66? You would go ahead and plug that 66 in for X. And then you would get 145.27. Now, we saw this actually on the last example, so it really didn't make sense that the dive time on the last example from the previous section was only 4 2/3 minutes. That has to do with the unreliability if you get outside of your observed data window. So like this, what would you predict the final exam score to be for a student who scored a 90? If I plug a 90 in for X here, okay, so negative 173 plus 51, or 0.51 plus 4.83 times 90, you actually get 261.19. Well, when we went over this example, the maximum score was 200. So we're predicting a score of 261 points, but the maximum score is 200. That's not really reliable. Has to do with because, again, we're predicting outside of the XYs in the observed data. Our observed data went from 65 to 75. So that 90 is outside of that window. All right, 12.6, outliers. In some data sets, there are values, which are observed data points, called outliers. They are far from the least squares line vertically. So like they're way above or way below the line, meaning they have large errors or residuals. The outliers need to be examined closely. Sometimes for a reason or another, they should not be included in the analysis of the data. It is possible that an outlier is a result of erroneous data. Other times, an outlier may hold valuable information about the population under study and should remain included. So the key is to examine carefully what causes a data point to be an outlier. Besides outliers, a sample may contain one or a few points that are influential points. Influential points are observed data points that are far from the other observed data points in a horizontal direction. So outliers are far away vertically. Influential points are far away horizontally. To begin to identify an influential point, you can remove it from the data set and see if the slope of the regression line is changed significantly. A rule of thumb for outliers is that any point that is located further than 2 standard deviations above or below the line of fit would be an outlier. Standard deviation uses the standard deviation of the residuals or errors. All right, so we are back to using that third and final example that we've used throughout a few times this chapter. So we can determine if there is an outlier or not by using technology. If there is an outlier as an exercise, delete it and fit the remaining data to a new line. So for this example, the new line ought to fit the remaining data better. This means the SSE should be smaller and the correlation coefficient ought to be closer to 1 or -1. So how to determine outliers on a graphing calculator. So I have already inputted my data here. I've already run my linear regression test and copy and pasted it into Y1. I need to figure out this standard deviation value. So to do that, I'm going to go to stat test, and I'm going to scroll down to the linear regression t-test. I don't really care about any of this. I'm going to calculate and scroll down until I see this This is our standard deviation, where we have 16.412. Okay, for the sake of trying to remember, 16.4 is what I'm going to round it to. So if I go to y equals, I need where 2 standard deviations above the line would be and where 2 standard deviations below the line would be. So I'm going to do vars, yvars function y1, and I'm going to add 2 times that standard deviation, which we found was 16.4. I'm going to do the exact same thing in y3. The only difference is I'm going to do -2 times that standard deviation that we found with that linear regression t-test. And then zoom stat to make sure it fits my data. So you can see this red line and this black line. That represents 2 standard deviations above and 2 standard deviations below the original linear regression line. And you can see this point here is an outlier. So if I hit trace, I can see that point in my table is that 65,175. If I hit up and down, it'll, left and right, I'll jump to the different points. Up and down will put you on the lines. So back to the points. That outlier was the point 65,175. So I'm going to say that that's an outlier because it is on the outsides of those 2 standard deviations. So if I go to stat edit, and we're going to delete that point out. That delete button is right here. So then I'm going to run my regression again. Stat, calculate, linear regression. I'm going to store it because I have to replace the old one in Y1. And what's nice is because of the way I set up the other outlier lines, those will automatically adjust as well. Except for I would have to change the standard deviation. So this R value should be closer to 1 or -1. In this case, it should be closer to 1 than what we got the first time we ran this to prove that it's a better fit. And you can see that the data does fit closer to the line now that we've removed that outlier. Numerical, the numerical identification of outliers. This table, so the first two columns are the same third and final exam data that we've been doing. Y hat, this is what would the prediction value be on that line of fit for each of the X's here. And then you would take the actual minus the predicted. So then we would still need that standard deviation, which again, it's just going to be easier to use your graphing calculator with that linear regression t-test. Remember that we found out it was 16.4. So we are looking for all data points for which the residual is greater than 2 times that standard deviation, so 2 times 16.4, or less than -2 times 16.4. So anything that's above 32.8 or less than -32.8. So if you look here, that residual actual minus predicted, this one is above that 32.8, which is the exact same data point that we found was an outlier by looking at the graph. And that is it for Chapter 12. As always, if you have any questions, feel free to shoot me a message. I will say the most common question I get with this section is, what's the difference between an outlier and an influential point? An outlier is far away from the data vertically. An influential point is far away from the data horizontally. So, like I said, if you have questions, reach out and I'm happy to help.